Well, good evening.
Jim,
Yeah, it's me.
give me a second here.
No problem.
Can you hear me?
I can. Yeah, can you hear me okay?
Wonderful. Yes, absolutely. Let me
Okay,
check
very
and make
good.
sure if this worked. It
Mhm.
worked.
Ah, that's good.
Yes, the role of Craig will be played by someone much more attractive tonight.
Wonderful, wonderful.
He
Yeah,
is.
I worked in the Boy Scouts with Craig for many, many years. So,
Mhm.
that's why he, looks to me and says, "Hey, can you do this or that?" But it's kind of fun being back with him again.
Yeah, absolutely. I remember one of your previous talks at
Oh,
ASRAS, and it
okay.
was
Uh-huh.
really enjoyed it. And
Good.
I love the Voyager missions.
Oh,
you know
super.
they did a documentary at one point that kind of followed the whole mission, and I watched that multiple times.
Wow, well, we're going to show some of it actually.
It's a fantastic documentary. Was very sad when they took it off of Netflix.
I know. Well, that's I'm going to show the JPL one.
Okay,
JPL made a documentary, and I'm going to show well just a little bit of it.
fantastic.
Yeah. So
So.
while I was out there, they played this documentary, and then when I took this position, they said, "Oh, you can use anything you want in that," and I said, "Okay, definitely, I'll use that."
Fantastic.
Yeah.
Um, oh, it is recording. Okay, I'm going to pause.
Thank you. Okay, thank you again. And it's great to see everybody tonight. And thanks for coming out. And tonight I thought we'd talk about Voyager. Voyager is a very interesting topic, and it just cuts across so many scientific endeavors from, optical astronomy to energy management and radio transmission and even how to repair a computer that's 15 billion miles away. We'll talk about that as well. So, me, I'm an ASRAS member, Jim Porter. I worked at NASA JPL as a contractor from Kodak and L3 Harris. But then I retired and I started doing this, the ambassador program. So, there's an image from one of my satellites that I help them build. That's from GOES-R that did caught an eclipse. I probably showed this to you the last time, where you can see the eclipse from 2020 as it crossed the Argentine-Chile beaches. And during my eclipse presentation, I actually showed it from the ground too. Okay, we're going to start the video. Let me know if you can't hear it right away. So let's just start it. T minus 10, 9, 8, 7,
We're
6,
good.
5.
In 1977, the greatest adventure in space exploration commenced.
We have ignition and we have liftoff. Our eyes, our minds, our souls are moving out through the universe.
You can only do things for the first time once. And Voyager kept doing things for the first time over and over again.
Two robots were built to be able to think and explore by themselves in the deep reaches of our solar system.
None of the managers really appreciated the complexity and autonomy that we just launched into space.
Yet both missions went seriously wrong only moments after taking flight.
We thought that we'd lost the spacecraft.
They went on to make astounding and unexpected discoveries.
When you see things that you did not predict, that's when there's the most to learn. We were just seeing that time after time.
The Voyagers were the creations of NASA's Jet Propulsion Laboratory, where a brash young scientist had just been put in charge.
I guess there's an obvious question, which is what about the lab itself? What about its people, its organization? Our sweeping change is imminent.
His ambition was to take the next steps in exploring the solar system. Instead, he found himself struggling for JPL's very survival.
And the greatest exploration was going on. It's the very time that the program was being strangled.
This is a story of triumphs
I just kept saying, what's that? What's that?
and setbacks.
I was no.
Most of all, this is a story of perseverance by people and machines struggling against forces put in their way. The stuff of dreams, beginnings of the space age. Next.
Yeah, so we're going to talk about that Voyager mission because it was such a groundbreaking endeavor for JPL and all of NASA. And as I watched that video, I realized that things really do come back around. And right this moment, the missions are being threatened. In fact, some of the budget changes, the sweeping changes, they're going to actually have to shut down some ongoing missions that are that we're really worried about, like New Horizons. New Horizons is just now, it just passed Pluto 5 years ago, and now it's out approaching, the Kuiper Belt area, and to shut a mission down like that, we just, it's just kind of mind blowing. We'll go through a quick history and we'll talk about a concept that JPL came up with called the Grand Tour. And we'll discuss some of the milestones, a lot of the discoveries that Voyager made in that first tour, especially Voyager 2, which completed the Grand Tour. We'll have a quick discussion on the anomalies because, man, it almost didn't go off. And for a mission that's already been running for 47 years, to think that it almost didn't leave the ground is just an incredible story of people, men and women that are able to overcome anomalies and get their vehicle back on orbit and into space. So there are some future missions inspired by this, by the Voyager spacecraft, and we'll talk about those. Some upcoming ones, hopefully, that will not get the axe. Because they are robotic, and so they're not manned missions, which the manned missions are still funded. But hopefully, some of the robotic missions at JPL will still continue. All right, so quick history of Voyager. In 1964, an intern named Gary Landro was at NASA JPL, and he was reviewing orbital data for the planets, specifically the outer planets. And he discovered that once every 175 or so years, the planets would have a, air quotes, alignment by which one vehicle, one spacecraft, could go to Jupiter, use gravity assist, and come around Jupiter and be on a trajectory to get to Saturn. Doing the exact same thing, we could use gravity assist at Saturn and get to Uranus, and same exact thing, we could eventually get to Neptune. Well, that is, it's not an alignment like you would think the planets are in a line, but this little graphic kind of shows what it effectively was. A single spacecraft could visit all the outer planets in a very efficient mission. So, of course, they developed that 4-year mission to get just to Jupiter and Saturn, which they were going to use both vehicles, 1 and 2, to fly to Jupiter and then on to Saturn. But the main target, if you go to Saturn, the main target for Voyager 1 would be the moon Titan. And it was very, very important to get a close look at Titan, because even here from Earth in the 60s, we could tell Titan was the most important object out there to study, being that it has a full atmosphere and is very large, bigger than our moon, and it could be a prime candidate for a place where we could have extraterrestrial life on board. So that was the main level 2 mission for Voyager 1. With that mission, Voyager 1 would only go to Jupiter and Saturn. So because of the orbit, it would then go from Titan's orbit around Saturn out of the solar system. Now, level 3 mission would be for Voyager 2 to go ahead and use that gravity assist at Saturn and go on to Uranus and Neptune, expanding the mission by 8 years and then completing the grand tour. So that was the objective. They only got approval for level 1 and 2, and they had to go on and prep for level 3, but they didn't get their funding until the last minute. So that was another one of the big the big endeavors. Now, question comes up right away. If you don't know what you're going to be discovering, what instruments do you decide you need? And so most of the scientists will say, okay, we need to cover the entire electro-optical spectrum. We've got to be able to detect everything from radio waves to gamma rays. And we're going to put a dozen instruments on board this spacecraft with the power supply and the computing power to be able to communicate this data set back to Earth. So that was their intent. And here is the instrument list they came up with. So for a cosmic ray detector would be on board, and believe it or not, both of those are still detecting cosmic rays after 47 years. A charged particle detector, again, still on. Magnetometer on board, still on. The plasma wave radio antenna, those are those very large antennas that you see protruding down from the vehicle bus, and those are still detecting plasma waves. The imaging cameras were turned off after passing by Neptune, so they're on the instrument boom, which is that boom on the top there in the image, with a wide angle and a narrow angle camera. And the infrared spectrometer and radiometer was also used right on through 2007. And the ultraviolet spectrometer was turned off very recently. And the radio astronomy for planetary to detect the magnetic fields, that was only turned off very recently. And the photopolarimeter never really worked correctly, although they did use it when they got to Jupiter, but it was of limited effect. So those were the 10 instruments, and there's Voyager's 1 on the right there. For the very first time, we were going into very deep space, the outer solar system, and so it needed to be rad hard for the very first time. If you're to orbit Jupiter, one orbit at Jupiter, if you go out to as far as Europa, that's the equivalent of about 1 million chest X-rays. So Jupiter, that it is the size of all the rest of the planets put together, has an immense radiation belt around it, and to fly through that is quite an experience. So for the first time, we had very large boxes, electronic boxes that were very thick for the first time, and it had to be a new type of software had to be written that would be self-repairing. It had to detect via its architecture and detect flaws and detect errors and bit errors, and it had to self-correct those. So they used 4 processors on board. It did have 256-bit chips on it, very low memory, and it did have a tape backup on board. Now, down at the bottom, you can see a new power supply that just was brought on for this mission. It's a radioisotope thermal generator and uses plutonium. It started out at 135 watts, so it's actually quite powerful for a spacecraft of this size. And to get the signals back to Earth, it had a 3.7 meter high gain antenna with 3 frequencies on the antenna mast that's in front of that big dish. So that's a 12-foot diameter dish that we need to keep that pointed at Earth. That's going to be the problem, keeping that dish pointed at Earth. There's the RTGs, we call them. That's a power supply that if you stack 3 of those modules, it's only showing 2 there, but if you stack 3 there, you can get about 150 watts Then it is converted to 28 volts for the spacecraft optimization, but it has to be placed far enough away from the instrument package that it will not cause interference. It's probably design life was actually in that 50-year range, and they certified it to 2025. So this unfortunately is the year that we're supposed to lose power on the RTG. So that would be end of mission at that point. But it is measuring about 40 watts, so it's putting enough power out right now to run the onboard attitude control and the computer and send back the comms are working and send back data to Earth. So so far so good. We haven't lost touch with the vehicle yet, although 2 years ago we did. So you just never know. People are always interested on the comm side of what that looks like. And so maybe I'm not sure if this group would be as interested, but you can see that the starting over on the left, the science data comes into a flight data subsystem, which formats and codes it for downlinking. And then there's a modulation system that actually will add a subcarrier to it and send out the telemetry to the radio itself. And the radio itself is a S-band. An S-band is 2 gigahertz, and it's an X-band transmitter as well. So X-band is, I believe, 5 megahertz. So the S-band and X-band then have a wide bandwidth and a narrow bandwidth antennas. So that's what's over on the right. The actual antennas, you can transmit high gain with the 23-watt transmitter. And at the end of that large dish, you've effectively got about 1,000 watts of transmit power from the 23 watts. So that's how much gain you get out of that S and X band antenna to get it back to Earth. So, we run all of our data and our command and telemetry through the system. It's all downlinked through this antenna system. And you can see here the low gain system is got a beam width of about 60 degrees. And so, of course, that X band, the high gain antenna, it's about a half a degree. So that's where you get your high gain to 48 dB, and which is effective about 1,000 watts effective at the end of the antenna. So that's how we get our data back from Voyager. But you've got to keep that half a degree pointed right at the Earth to get the signal. Now, how are we getting it? Well, we're using a 230-foot dish. We've got 3 sites around the Earth, all, basically 120 degrees apart so that we get full coverage 24 hours a day, anytime we need to reach one of the Voyagers. This is the picture of Goldstone, California, which is in the desert right outside of Pasadena. So you can actually go out and go to the visitor center over there on the left, and they have a great tour. And you can see some of the dishes, take a tour of the they've built that dish right there for the Mars mission, the first flyby of Mars. So that's the reason we had that dish. Now we've got one in Spain, and then of course Australia. So those are the 3 locations we use for the Deep Space Network. It's a 40,000 square foot surface, and it is sensitive down to 10 to the minus 18 watts. So you can imagine you're transmitting a 23 watt radio, even though you're using a big antenna. It's 15 billion miles away, and even the most powerful radios will have to struggle with that. So you have to design a receiver that is cryogenic, extremely sensitive, down to 10 to the minus 18 watts to be able to receive that signal. So that's where we get the data at Deep Space, and you can go online to Deep Space Network and watch them downlink the data. It's kind of fun to do that, actually. Sometimes I show that slide. Now, one of the controversial things about sending Voyager was they knew it would leave the solar system. So they made what we call the golden record. And the golden record, if you look on the upper right, is the sounds of Earth. Now, it is kind of interesting to think that, an alien civilization would actually have a record player, but, who knows? This is what Carl Sagan decided to do. He was selected by NASA to form a committee and figure out which 55 languages we would put on this. And of course, a message from the president, hello, we're here. The controversial part is over on the left. If you look on the left, upper right of the back side of that record, that actually shows where we are. So those are, I haven't counted them, but 2, 3, 4, 5, 7, 8, 10, about 12 pulsars. So those are located in the Milky Way, pulsars, and it shows right where we are. So the question, of course, you would want to know is, was that a good idea to show the alien civilization right where we are? But that's what we did with the golden record. So that's on board Voyager 1 and 2. Let's talk about some of the discoveries. A lot of milestones. As the video said, they did a lot of things for the first time on this mission. They're going to find volcanoes. They're going to find geysers. They're going to find the Earth. They're going to find some amazing sites out there.
For 7 years, we'd been preparing, and suddenly, for a period of several months, we were overwhelmed with flood of discoveries, one after the other, many every day. One of the challenges we have in planning, because all this has to be pre-planned, it all has to be loaded onto the spacecraft and then executed automatically. What do we look at? When? What do we observe at what time?
Stone knew that taking the position would mean coping with sizable squabbles among a science team numbering over 200.
I think the point is that we don't want to work the problem here. If there are some problems, there's an outside forum to do it. That's
Sure. It was a great training ground for learning how to handle conflicting science requirements. There's a phrase that shows up in discussing science conflicts.
Yeah.
My science is better than your science. And if that's your only argument, you're not going to win. You've got to convince the other guys that you've got a point that your science is worth doing and it's worth trying to accommodate it.
I remember being in the ops center at the first Jupiter encounter and seeing these pictures returned in real time, an image every 42 seconds, downlink from the spacecraft, at these odd-looking worlds, just blew us away. And I really experienced the sense of discovery.
As we approached Io, we saw an object that looked unlike anything we'd ever seen before. In fact, we have not seen anything like it since. We did not understand what we were looking at all. It was so different than anything we had imagined. And it was only as we were flying by Io that a navigation image was taken. That is, an image taken with a deep exposure to find the stars in the background. The navigation engineer, Linda Morabito, noticed that there's this large plume off the limb of this little moon of Jupiter.
The phantom moon turned out to be a gigantic plume of gas and dust, shooting skyward from a volcano.
And that was the first indication that this is the most volcanically active body in the solar system, 100 times more volcanic activity than Earth. And yet it's just a small moon orbiting this giant planet.
All told, the two Voyagers took more than 33,000 images of Jupiter and its major moons. What these images and the other science results revealed was an exotic system that was not only vast, but beautiful, and almost beyond imagining.
those images are still amazing and stunning. In 1979, I can only imagine how amazing and stunning they were to get those images back, especially looking at the moon Io and suddenly realizing you've got this moon that's trapped in this gravity field that's just squeezing it like a tennis ball. And that interior is just a fluid that's being compressed constantly. And we have over 100 active volcanoes they've discovered. Of course, they passed by Io and realized that it had all these striations and it was a snowball, a white snowball, and that it was actually cracked ice. And then, of course, the spot, counter-rotating storm. They got a really good look at that, and they found some two new inner moons that they didn't expect that were very close by. And of course, that picture on the lower left was a big surprise that Jupiter has a ring system, and it can only be seen from the back. It doesn't really light up in from the front with solar illumination. You've got to see it from the back, and that's what that picture is. Where they picked up on the ring system. So amazing discoveries there at Jupiter. And of course, Europa has been just intriguing ever since that visit in 1979. The Galileo probe spent quite a bit of time investigating Europa, and Juno, which is there now, the Juno probe is actively taking imagery. And of course, the Europa Clipper is the new mission launched last October, and it will specifically be doing science at Europa. Europa is a tidal forest moon. It has an elliptical orbit. It does also get squeezed, and that's why that ice shell is flexing. And that is why the cracks are forming, and the cracks do move around. And that's why it's intriguing to try to understand what is underneath that moon. That'll be Europa Clipper's main focus when it goes out there in a couple of years.
As Voyager 1 bore down on Saturn, the spacecraft was clocking nearly 1 million miles a day. And each day, Saturn revealed itself in some new way.
Among the tremendous surprises there was that we could be, still more than 1 million kilometers away, and we could see structure in the rings.
Hey, look at that.
More and more, the rings were revealing their intricate and baffling structures. For many scientists, the moon Titan was as important as Saturn itself. Titan is so large that if it orbited the Sun rather than Saturn, it would be called a planet. It was already known that this was the only moon in the solar system having a substantial atmosphere. This might be a place, some scientists theorized, that resembled the Earth before life arose. And that made this moon an irresistible target. But getting the best possible views came with a steep price. It required Voyager 1's tour of the planets to end at Saturn. That was the choice made, for Titan was deemed that important.
Well, there was this great hope that we'd be seeing down to the surface through this thick atmosphere, and we would discover, amazing things. As we got closer, at the time when we should have started to see features and resolution, it was awfully blank.
Although the hazy images of Titan were disappointing, the atmosphere was found to be, like our planet, rich in nitrogen. As hoped, this was in some ways a primordial Earth. After Titan, Voyager 1 swept underneath Saturn and then rose up out of the plane of the ecliptic and headed up towards interstellar space.
So that's the end of the Voyager 1 mission at Saturn in 1981. It was an amazing set of discoveries. If you look in the lower right, for the first time, they realized that some of those those divisions in those rings were because there were actually shepherd moons in the ring system. They, spent that time at Titan to try to understand that atmosphere. It is about 20 pounds per square inch absolute, so it's about 1.5 times the density of the Earth's atmosphere and completely nitrogen. And so that is actually going to inform some of the next missions. It certainly was a big part of the Cassini mission when they landed a probe on Titan via parachute. It took 3 hours to parachute down through the Titan atmosphere. It is 1/3 our gravity, but 50% thicker atmosphere. So, of course, over on the left, Enceladus was again found to be a snowball planet and a very intriguing planet or moon, I mean, a snowball moon, and a very intriguing one. A lot of thoughts about that. And Cassini spent quite a bit of time later on looking at Enceladus. So lots of pictures came from this visit. I love that one in the upper right. Saturn really certainly put on quite a show for for Voyager 1 and 2. There's a cutaway of what we think Titan looks like, and of course that's Cassini, the deep space probe that went there in '99 and visited in 2006. But you could see it's very, very probable that there is a lot of water on this moon. So very much a place where we need to go back to. If you were to compare the two, there's Earth versus Titan right there. And the nitrogen atmosphere on Titan, of course, is pretty cool there. 292 below for Fahrenheit. There's a picture on the upper left looking down in through the clouds. Cassini took that picture and they named that lake Lake Ontario. So it looks just like our Lake Ontario. See, there's the Genesee River going in there. And of course, the liquid cycle on the surface Titan at that temperature is a methane liquid cycle, but it is absolutely loaded with organic chemicals. So even though it's different temperatures in the surface materials, underneath that surface is something that we really want to take a look at. So that again will inform future missions. There will be one very shortly headed to Titan to take a look at those some of those areas that we want to look at the crust of Titan. Okay, so this is the Huygens probe that landed there in 2005 after that visit. Again, as I mentioned, it parachuted in, took 3 hours to land, soft landed in a lake bed. And if you look in the color corrected version of that picture on the left, over on the right, and it just looks like it might be the shore of Lake Ontario, even though they were eroded with liquid methane and liquid ethane. It's pretty amazing when you get to the surface and you see an image like that on the right-hand side. Enceladus was an amazing target because when they flew by, they realized there were active cryo geysers at the south pole of this ice ball moon, telling us right away that obviously this is also being gravity flexed by the surface. The ice surface is being flexed by the gravity of Saturn, and it is creating these geysers at the South Pole. And so immediately, one of the missions for Cassini was going to be to fly through that and tell us what that is. And of course, they did accomplish that in 2002. And lo and behold, it's salty water. So very intriguing. And boy, a lot of NASA astrobiologists can't wait to get a mission back out there sometime in the next few decades. Okay, onward to Voyager 2 to Uranus. I don't have a video on this, sorry about that, but Uranus was discovered to have 10 moons, and it has a set of rings, 7 rings, and within those ring system, they found some of the moons, shepherd moons, just like at Saturn. It's has this axial tilt, which we knew before that it had a 98-degree axial tilt, so it's rotating on its side. But the magnetic field does not obey the axial tilt. And so that's another intriguing fact. It's a 59-degree. And so it sort of corkscrews around the planet. So again, more science to go. This is the only visit that NASA has had, 1986, Voyager 2 visiting Uranus. So, of course, a lot of scientists would love to go back out there and do another mission where we can maybe orbit Uranus, try to figure out what happened out there, what's going on with the magnetic field. And again, really interesting discoveries. And of course, in '89, at the end of Voyager 2's planetary mission, we got the Neptune. It is extreme environment. It's an ice giant planet, so it's a frozen solid. It's got the coldest temperature ever measured by a by a by a radiometer in space, and that was on the surface of the moon Triton, and it is minus 391 Fahrenheit. So we're getting pretty close to zero out there. Triton was also found to have some craters, but was also spewing material out of the South Pole. So a very similar moon to the moon we took a look at Enceladus at Saturn. So very interesting getting out there. Again, the only time we visited Neptune, 1989, via Voyager. Here's a cross section of what we think that moon looks like. Looks almost the same thing as Enceladus. So a rocky core, a global ocean, an ice crust at that temperature at the surface, but yet, because it's orbiting a gigantic planet, that ice crust is flexing due to its tidal forces, and it's got active geysers at the South Pole. Wouldn't we love to be able to fly through those geysers with a probe and detect what's on the interior of a moon? That moon is 2.8 billion miles from the sun. So it's just amazing that we can get imagery like that of a moon that far away. So, of course, both Voyagers continue to operate, and now it's 47 years later, and Voyager 1 is approaching its end of life. It's 5.5 billion miles from the sun. That is a real-time image from last October. It's not an image, it's a real-time simulation of where it is. It's above the ecliptic, as we mentioned before. You can actually get a live view of this, of where they both are. I only picked the Voyager 1 image. Voyager 2 wasn't quite as interesting, but this also had New Horizons in it. And so that's one of the reasons I picked this one. There's the New Horizons mission, which went to Pluto in 2016, and it is in the ecliptic and is also entering the Kuiper Belt. So Voyager 2 is 13 billion miles away. And eventually, maybe somebody at a star named AC 793888 can play that record, because in 40,000 years, Voyager 1 will pass only 9 trillion miles away from that solar system. In 300,000 years, though, Voyager 2 will get to Canis Major. So it'd be close, only 25 trillion miles from Sirius. So they're still out there. They're still taking data with some of the instruments, still taking that data and relaying it back to the Deep Space Network back on Earth. So, as we mentioned before, and it was in the video, that there were some anomalies and setbacks. Some of them happened right away, right on launch, and we learned quite a bit during these.
2, 1. We have a mission. And job of the Titan Centaur carrying the first of the Voyager spacecraft to extend man's senses farther into the solar system than ever before.
Voyager's programmers had taught the spacecraft that if it sensed anything unusual, to switch to backup systems. And that's exactly what had already occurred. Engineers call this Fault protection.
The fault protection started doing its thing, reconfiguring the system. We're still attached to the launch vehicle. It's in the early stages of its flight. And the first thing we see are the gyros being swapped.
The launch vehicle, as part of its powered flight, went through a roll. And the spacecraft would never have done that on its own, so spacecraft thought that was a fault.
I think there were 6 or 7 different states that it went through in trying to correct the fault. Well, soon I can't have 2 gyros fall. It must be a computer that has failed. No, it switched out. We had redundant computers, so it switched out computers. Well, it can't have been that. It must have been something else. So it went through this whole sequence of trying things. And we thought, holy mackerel, this spacecraft looks like it's gone bonkers. And we thought that we'd lost the spacecraft.
Finally, we got to separate from the launch vehicle and we were on our own, but the problems weren't over.
The spacecraft was now slowly tumbling.
Well, I've actually had things like this happen on vehicles that we've designed, and I tell you, one of the very first things we learned from this mission was you do not leave your attitude control system on during launch because it is not in charge. And the launch system is in charge, and you have to wait until you separate before you initialize some of your computer, specifically your attitude control system. So we also had an issue on the second stage. It wasn't just that tumbling issue, which, by the way, they just because eventually that wideband antenna I showed you, the 60-degree antenna, would come into range, and we could reinitialize the attitude control system and slow that tumbling down. Voyager 1 basically had a second stage issue where some of the hydrazine, the propellant on the second stage, had been leaking during launch, and it did not quite get the trajectory they were hoping for. So it was a little late when it got to Jupiter. Now, that's a pretty wild ride. That I've sent several vehicles on, more than several actually, on the Titan Centaur system, and that is a 9G liftoff. And it's got a lot of low frequency content in its in its dynamic response. So it is quite a shake to a vehicle like this. So I can empathize with those guys. So Voyager 2 in 1978, for a period of time, it went offline. The spacecraft had switched to its backup radio receiver, and sometime afterwards, the primary receiver failed altogether. Again, this was the very first month of the mission, and I had a capacitor. This is what does happen. That's why we have redundancy on board, and it could only receive transmissions that had a very precise frequency control from Earth, and so we had to actually rewrite the upload algorithm so that we could communicate with Voyager 2. So that was another very interesting impact of launch via this launch system. It is, again, a very, very tough system to work with. If you do recognize that vehicle on the right, that is what we used to launch the Gemini spacecraft on without the solid rocket boosters. But we use that quite extensively for some of our deep space missions. Okay, so just recently, that's a picture of the processor there in the upper right. And you'll see it has those memory chips in the far upper right, and those memory chips are 256-bit chips. And in 2023, Voyager started sending back garbage data, basically nonsense. And so they realized that the computing system had a fault and it had a failure in it. And it was eventually going to lose contact with the Earth if we couldn't figure this out. And so they did a memory dump of the flight data system. And in that memory dump, when they got it back down, now it does take 27 hours to get that signal back to the Earth. When they got the memory dump down, they mapped it and found that there was a range of memory that was missing from the dump, and realized that, okay, one of the chips is bad, but there was no one around that could actually reprogram the flight data system. So they brought an engineer in out of retirement, and he was just a young guy when they coded that in 1975. And he was able to recode that and map that memory location out of the flight data system. And they then went ahead and sent the signal back up there without that chip in its memory map. And when they waited for 27 hours, and believe it or not, they finally got a signal back that the computer reinitialized, and they were back in business. So if you can imagine trying to fix your computer from a billion miles away, those flight algorithms and the computer, the programmers at NASA are some of the best I've ever seen. I actually worked with quite a few of them over the years and had really great experience with their computing team. Okay, so I promised section 4, we'd talk about what were the follow-ons. And of course, we mentioned Cassini. Cassini spent 13 years reinvestigating all the discoveries of Voyager 1 and 2 at Saturn. And we have Juno now orbiting Jupiter every 53 days. And it is especially looking at these water worlds, not just Europa, Ganymede and Callisto as well. We call them water worlds because they actually have more water than the Earth has. And it's pretty amazing to study those right up close. Now, Juno is interesting because it's the very first solar-powered deep space probe. So those solar panels are the very high efficiency panels that NASA designed several years ago in the 2010. They're about 60 feet long. So each one of those sets of panels is about 60 feet. So it's a pretty large array, so much larger than what we might have on a near Earth or a low Earth orbiting vehicle. Of course, and launched last October, Europa Clipper, and that one is going to orbit Jupiter and fly by Europa every 50 days. And again, it's another solar probe, and those solar panels are over 100 feet long. So that is a high-powered unit, if you will. And it's got lots of high-resolution cameras to map the moon and detect its atmosphere. What we really do want to do, of course, is ice-penetrating radar, study the interior of the moon. Thermal camera, try to image places where it might be warm on the surface, which would indicate thin ice, and that would be where we'd really like to investigate in the future. And study the chemistry and the dust that's around that moon and what's attracted to the moon. And study the atmosphere. As I mentioned before, it does have oxygen in its atmosphere. The oxygen is produced because that's water on the surface and it's in a high radiation environment. And so obviously we've got some electrolysis going on the surface. What I mentioned before was the fact that in 2027, we hope to send not a rover, but a rotocraft lander. So it's called Dragonfly. It looks very similar to a Mars rover, but it will be a rotorcraft or a drone. That is a very large drone. That's the size of an SUV. Those propeller blades are about 6 feet long each. There's 8 of them. And as we mentioned before, the surface of Titan, you have a 20 psi atmosphere there and a 1/3 gravity, so it doesn't take too much to fly around on Titan. And so even though that's a very heavy lander, we have no problem. We actually have one of these flying in a chamber to determine how we're going to fly this on Titan. Of course, we are looking for on Titan a ice penetrating impact crater. So we're looking That mission will be looking for a crater that has impacted and gone through the ice shell on Titan and has exposed the water that's underneath that ice shell. So you can see in this image some of that liquid has been splashed out onto the surface and conveniently freeze dried for us. And so that is the primary target for Dragonfly and the future mission on Titan when it does eventually land. Okay, so that kind of brings us to the end of our discussion tonight. I hope it was entertaining and interesting. And if anybody has any questions, I'd be willing to stick around and we can talk a little bit about it.
That's a great presentation, Jim.
Hey, thanks.
So, Jim, a couple of years ago, one of our members asked the crew that are still monitoring Voyager 1 to see if they could monitor a gamma ray burst that we had detected somewhere.
Yeah.
Voyager was actually able to dig into the data that Voyager had already sent back to verify the gamma ray burst, and I guess they got a little bit of information out of it.
Isn't that fascinating? Those cosmic ray detectors are still working.
Yeah.
After all this time.
This was 2023, I think.
Yeah.
October, November 2023. Pretty amazing.
Yeah. Yeah. What's one of the interesting facts about Voyager is Dr. Stone, Ed Stone, the project manager, he's still on the program. Yeah. And so, there's been an amazing consistency.
I think that's the guy he was talking to.
Doesn't surprise me because it's a very small office. There's only a handful of people in the office.
Oh no, it wasn't Stone. It was Eric Burns and Alan Cummings. Caltech guys.
Yeah. Well, Caltech runs the lab, so.
Yeah, pretty interesting stuff. He had brought a little information to one of our meetings and showed.
Oh yeah, very good.
Peak of the gamma ray burst as it was happening.
So of course, what is the cosmic ray density out there? That is one of the really interesting questions that Voyager is helping us with.
That would be the big part of its mission at this point, I would imagine.
Right. Anybody else have any questions tonight?
Yeah, I've got a question. This is Don Chamberlain. I've heard the term used, and I don't know what it is. You mentioned a propellant called hydrazine.
Right.
Now, is it some kind of a cold propellant that you just squirt out? Or,
yes.
Or is it a
auto-combusting propellant? Exactly right. So hydrazine is highly toxic. It can only be used out in space. You don't ever want to bring any back. You want to exhaust it completely. And it was very commonly used in early spacecraft second stages and third stages. So a lot of times when we used to bring the shuttle back, we had to make sure that if it had a satellite on it, it had exhausted all of its hydrazine propellant. So yeah, that's the that's the bad actor.
Yeah. So it's not something that you ignite, but you squirt it out.
Right.
Yeah. Okay.
Yeah. Auto ignition.
Yeah. Yeah. Thank you.
Yeah.
Mm-hmm.
I have a question. Can you hear me?
Yeah.
Yes. So what kind of solar cells are being used? Are they multi-junction cells made at JPL?
Well, that's an interesting question. I haven't really investigated that side of it. It is not the gallium arsenide though.
Okay.
It is a triple junction high density cell. But that's a great question. We should probably go back and take a look at that. Especially on Europa Clipper, those are the very high energy cells that they put on there. And of course, we learned all this. We learned how to do all this from the International Space Station, which has kilowatts of energy. I think it's 12 kilowatts it can generate from those huge solar panels that are similarly hundreds of feet long.
Wow. Yeah.
Yeah.
No, they're multi-junction. They are very high efficiency cells. Yes.
Mhm.
So we'll look into it. Thank you.
Okay.
Thank you.
Those panels are taller than the Statue of Liberty. They're very, very long.
They're radiation hard also.
Yeah. Yeah, that's going to be one of the issues.
Mm-hmm.
Anyone else have questions for Jim?
Thank you. Very nice talk.
Great presentation, Jim.
Okay, thanks
honestly.
so much.
Thank you very much.
All right,
Appreciate
everybody,
it.
thank you so much. Really appreciate you coming tonight. I hope you enjoyed it. I think it was a fantastic presentation. And Jim, thank you again for just taking your time today and sharing your knowledge.
Absolutely. Thank you for having me. We'll be back sometime next year, hopefully.
Sounds great.